Gas laws. Na 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 na. Gas laws. Na 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 na. Gas laws. Hello, ladies and gentlemen. Today we're going to discuss the ideal gas laws, or the more serious side to whoever smelt it, dealt it. In our first step, we must discuss Brownian motion. You could just say that all of these jokes just kind of writes itself, doesn't it? So Brownian motion is the random motion of particles, and the key word here is, of course, random. This explains why particles behave the way that they do. It was discovered by a botanist named Robert Brown, and with this discovery, Einstein was able to help explain the kinetic molecular theory. So Robert Brown was a botanist that discovered Brownian motion, and Einstein came along and he described it as this thing called a random force. And so we see Robert Brown down there. He doesn't look too happy, a little disgruntled, you might say. And so the reason why is he wanted to, as a botanist, study some pollen. And so what he did is he got some pollen and he scraped some off. He put it on a little microscope slide, put some water on top of it. Now, when he did that, the pollen was light enough that the tiny little motions of the water molecules would bump and razzle the pollen around. And so he couldn't actually focus on the pollen molecules, just like what you see in the image down there. The pollen molecules will be just jittered around, and so he couldn't, properly conduct his studies. But in turn, he did discover Brownian motion. So we can see Brownian motion whenever we see smoke. See, smoke particles are very light, and the particles in the atmosphere, however they're moving, will jostle the smoke particles around so that when the molecules in the air hit the smoke molecules, it creates these twists and turns. The direction of the motion can be affected by the air molecules, and more specifically, the net momentum. Okay, so this is why smoke seems to appear to just move randomly, and we can see that in the image down there. The big yellow circle is what we can consider to be the smoke particle, and all the tiny little particles that you see there, don't stare too long, it might make you sick, are the molecules in the air. And the molecules in the air bump into the smoke molecules, making it move this way and that way. All right, so the first on our list of the gas laws is the law for pressure, or we need to know about pressure, which is the force divided by the area. All right, first up, we have Boyles Law. In our lower left-hand corner, we see Mr. Boyle himself looking ever so fancy in the high socks and the wig. So he said that PV, or pressure times the volume, is constant when the temperature is held constant, which we can see right there. And so what this gives us is a inverse relationship. For example, if pressure goes up, volume has to go down, and vice versa. And we annotate that like this. That kind of looks like an infinity sign. About 20% of it is missing though. All right, and if we were to graph data looking at Boyle's Law, it would look something like this. And we're going to look more into these kinds of graphs, but let's take a look at this shape. This shape says that as the volume decreases, the temperature increases. Okay? And as we increase the volume, the pressure also decreases. And that goes along with Boyle's Law. Here we have a simulation that shows why this happens. So we have a constant temperature, and we can see that as the temperature and the heat heats up the molecules, okay, the molecules are going to jostle around, but we can add more mass to it, okay. So if we add more mass to the container there, it's going to decrease the volume, and when the volume decreases, the pressure is going to increase because all of those tiny molecules are going to bump into each other. So in conclusion, as the volume decreases, the pressure increases because the air molecules are not allowed to move around in a great amount of space. Because of this, the collisions that the molecules have within that container per second increase. So because there's more collisions, the container will feel more pressure. And next up, we have Charles's Law. Charles' Law says when pressure is held constant, the temperature and the volume varies by a ratio, which is also a constant. And we can write Charles's Law out like this. With volume in the numerator and temperature in the denominator, that's a ratio, and that ratio will always be held constant. For example, if we wanted to increase the volume, the temperature also has to increase in order to keep the ratio the same. And in order to write this, we can symbolize it like this. There's a direct correlation between volume and temperature, as long as pressure is held constant. If we were to graph it, it will look something like this. As the temperature increases, the volume increases, and vice versa, a direct correlation. Here we have a simulation that shows exactly why this happens. So the pressure is held constant, and we know this because the green masses remains at 2. And so what we can see the simulation doing is that the fire or the temperature gets bigger. The temperature increases, and when that happens, the volume increases. And in order for this to happen, the temperature also has to increase. So as the temperature increases, the particles gain kinetic energy, and it gains kinetic energy from the increase in temperature. When the particles have more energy, it collides more and more and more per second against the container. And when this happens, the container has no choice but to expand because we're not holding the volume constant. All right, last but not least, we have the pressure law found by no particular scientist. And so I put a picture of David Bowie and Freddie Mercury, who sang the song Under Pressure. And they said once, when volume remains constant, the pressure and temperature will have a ratio. And we can write it like this. We have pressure in the numerator and temperature in the denominator, and that is a special ratio that will always remain constant. And once again, from the other law, we know that when we have something in the numerator and in the denominator, and they both equal something constant, they have a direct relationship. And we can write that like this. So as the pressure increases, the temperature also has to increase. And we can designate that in a graph like this. As the pressure increases, so does the temperature. Now, if you want to think about this, try doing this. If you squeeze your hands together really, really tight, that's a very bad example, but it gets the job done. The temperature between your hands, the temperature increases. Think of it like that. All right. The reasoning behind this is in a fixed container, the container has a fixed volume. So if we increase the temperature, you're giving the particles more energy. And the more energy the particles have, the more will collide with the walls, thus increasing the pressure on the walls. It's just going to keep on pounding on the sides, and so the pressure has to go up. All right. Now with these three laws, we can combine them into one. P times V divided by T has to equal to a constant. And we can also write it like this. P initial times V initial divided by T initial is equal to P final times V final divided by T final, where P is pressure, V is volume, and T is temperature. And it's kind of like this, the Deathly Hallows. With three very powerful things, you can combine into one even more powerful thing and conquer death itself. Conquer the physics exam. All right, there we go. All right, so in summary, we have Boyles Law, which requires constant temperature. P initial, V initial is equal to P final, V final. We have Charles's law, which requires constant pressure. V initial over T initial is equal to V final over T final. And last but not least, we have the pressure law, which requires constant volume. P initial divided by T initial is equal to P final over T final. Now, with all of that, we can come up with this thing called the ideal gas law. And what you see on your screen is a very long form of it. In fact, it's two equations combined into one. And it's describing the ratio of pressure, volume, and lowercase n is the number of moles. R is what we call the universal gas constant. It is the amount of energy per amount of particles times its temperature. Capital T, of course, for temperature, which is equal to capital N, which is Avogadro's number, Kb, which is Boltzmann's constant. Okay. Now, those two equations, we can write it as PV equals nRT, or PV is equal to nKT. Okay. And I will teach you when you can use either one. So the man on our right is Mr. Boltzmann himself, handsome as ever. So PV equals nRT is used on a macroscopic level, meaning we're looking at a lot of gas, okay? More than 1 mole of gas. PV is equal to nKT is used on a microscopic level, not a lot of gas, so like a small sample of gas, okay? So Boltzmann's constant is a ratio that all gas molecules have. And this is simply an astounding discovery. It is the ratio of kinetic energy and temperature contain each molecule of gas. So in summary, if a gas molecule's temperature goes up, the kinetic energy that gas molecule also goes up, and vice versa. If we take away kinetic energy from a gas molecule, the temperature of the gas molecule has to also decrease. And Mr. Boltzmann found that for all gas molecules, it holds the same exact ratio.
The equation we see right there is the equation that we can use to determine the kinetic energy and the temperature for a gas sample. All right, now with all the physics out of the way, let's get into the more important stuff, the gas laws that we should all abide.
Whoever spotted the Delta, he who declared it, blared it, he who observed it, he who detected, rejected it, he who rejected it, respected it, he who said the right to the crime, whoever spoke last out of the blast, whoever denied it, so defined it, dispeller is a feller, he who introduced it, produced it, whoever spoke defines is smoking death, he who accuses, who accuses, he who refuted it, he who argued, persecuted it, whoever spoke broke it, whoever had spoken the word, he who declared it, blared it.
Ladies and gentlemen, those are all of the world's gas laws.